All right, let's look at how we solve the homework complex problem, the second one. Right, so the first one I did in another video. This was the homework that I had assigned to you. I'm going to kind of walk you through how you would go about this. So, very first thing you want to do in a complex circuit that includes LEDs is check your LEDs and see which ones are wired incorrectly, if any. So if you look at this diagram, we have our battery and we have current that's going to leave and travel all through R1. It will get to this junction and some of the current will go up and the rest of it will go around and up through R4. Okay, but let's go back to the junction. So at this junction, we see that we're going to come to two LEDs. So here's another junction, right? The current has a choice which way to go. And so here's you have to look at how these are wired. Right, you have two LEDs, one of them is wired improperly. So remember, you want the cathode of the LED to be connected to the negative side of the battery. So this L2 is wired correctly. L3 is not. So no current will travel through that part of the circuit. So all of this current is going to go through L2 and then it will get to this junction and then it will have a choice which resistor it goes through. Okay. And then at the top, you have current that's going to start to meet up together, and then all of the current will travel through L1 and go back to the battery. Okay, so the very first thing we need to do is start finding the equivalent resistance by working kind of from the inside out. So I'm going to deal with R3 and R2 first, right? These are wired in parallel with one another. So I'm going to find the equivalent resistance between those two resistors. So if they're in parallel, we're going to take the inverse. So 1 over R2 plus 1 over R3 equals 1 over, since they're wired in parallel, I'm going to call this RP. So I'm not going to show my work, but I'm going to talk you through it. So I have 1 over R2, which is 6 ohms, plus 1 over R3, which is 10 ohms, and then take the inverse of that, gives me RP as being equal to 3.75 ohms. Right? And so what I've done here is take R3 and R2 and essentially turn them into one resistor. Right? Now, if you think about me doing that, I don't want to erase my diagram because we're going to need it in the future for future parts of this, but it's kind of like there's just a resistor in here, RP, and that's connected to L2. So those are in series with one another. So I'm going to find the equivalent resistance between those. So I have RP plus L2. And that is going to give me the equivalent resistance. I'm going to call that RS because they're wired in series with one another. So RP we found to be as 3.75 ohms plus L2, which is 11 ohms, gives me a resistance here of 14.75 ohms. So that essentially is this entire middle. So I'm just going to draw a quick sketch of what we still have here. Right? So I still have R1 down here. We have this piece, and I've just turned this entire middle into essentially RS. Right? And then we still have this LED, and we still have R4 on the outside here. Okay, so really what I did was just work with the middle and come up with RS as being 14.75 ohms. Now, this is still wired in parallel with R4, so that's my next piece. So I have 1 over RS plus 1 over R4 equals 1 over, let's call this 1 over R, Y, right? The letters don't really matter here. So 1 over RS. So RS was 14.75 plus 1 over R4, which is 16, will give me 1 over RY, and then we're going to take the inverse of that. So 1 over 14.75 plus 1 over 16. Take the inverse of that. Whoops. 1 over goodness, 1 over gives me Ry as being 7.67 ohms. So I've taken these two and turned them into Ry. So I have left here my battery. I have R1, I have Ry, and then I have LED1. Right? So this is R1, this is Ry, and this is L1. So now I have a series circuit left. So series circuit, you're just going to add them together. So Req, the equivalent resistance of the whole circuit, will be R1 plus Ry plus LED1, which is 9 ohms. Well, I can just put in here L1. All right. So equivalent resistance will be R1, which is 4 ohms, plus Ry, which we just found to be 7.67, plus LED1, which is 9. So we add those together, gives me an equivalent resistance of 20.67 ohms. Okay, and now the second part of part A wants you to find the total current that will travel through this. So now I'm going to use Ohm's law for the circuit as a whole, right? So this is Req, and I know the total potential is 12 volts. We're looking for I, and my equivalent resistance was 20.67 ohms. So that gives me a current of 0.58 amps. So that is something that we are going to need to know. So I am going to add that to my list of givens here. So I know that my total current is 0.58 amps. Okay. So that was part A. Now part B wants you to find the current that will travel through each resistor. Okay. So we want to find current in each resistor. So R1 should be pretty straightforward. All of the current is going to go through there. So R1, my current in 1 will be 0.58 amps. Okay. Then we have current that's going to split, right? And all of that, whatever splits, is going to go through L2, and then some's going to go through R3, and some's going to go through R2, and then you also have R4 to deal with. So we have to look at the resistance of each of those paths and how the current is going to split. So the very first thing that I would do is look at the voltages. So I want to look at the voltage, the potential drop of R1, because that's going to help me determine the potential of R4, which will help me determine the current of R4. So I want to find V1. Okay. So to do that, I'm going to look at using, let's do this down here. V1 will be equal to the current that travels through that. I'm just going to call it I1 times the resistance of that. So V1 is equal to all of the current is going through this, so 0.58 amps, times the resistance of R1, which is 4 ohms. So V1 is equal to 0.58 times, what do we have there, resistance 4, 2.32 volts. Okay, so I'm just going to write this here. This is 2.32 volts. Okay, and it's going to go here, it's going to split. Whatever current decides to go through here, some of that potential will get used here. I'll call it V4. And then you also have L1 to deal with. So I want to find the voltage here as well. Now, all of the current is also going through there. So I'm going to find the potential drop over L1. I'm going to use the current that goes through that, which is the total current, times the resistance of L1. So I have V of L1 equals 0.58 amps times the resistance of L1, which was 9 ohms. So 9 times 0.58 gives me a potential of 5.22 volts. So I'm going to write this up here. So this uses 5.22 volts. Now, if you just choose the path of going through R4, so current is going to leave the battery, go through R1, it's going to decide to go through R4, and then it has to go through L1 and back. So the total potential along that journey has to be equal to the total potential of the battery, which is 12. So to find the potential of V4, I'm going to start doing some of this work. Let's do it here. So V4 will be equal to V total minus the voltage of resistor 1 minus the voltage of LED 1. Right? So the total essentially is the sum of these three, but I've just solved for V4 here. So V4 will be 12 minus 2.32 minus 5.22. So 12 minus 2.32 minus 5.22 gives me a potential around resistor 4 of 4.46 volts. Now, that helps me determine the current that will travel through that, because I can find the current through resistor 4. I know I'm doing them a little bit out of order, but this is just easier to do. Right? So we can use V in resistor 4 equals the current through resistor 4 times R, the resistance of resistor 4. And we just found V. So this is 4.46 volts equals I4, which is what we're trying to find, times the resistance of resistor 4, which was 16 ohms. So the current through resistor 4 will be 4.46 divided by 16 will be 0.2, let's round, 28. Right, so here's the total current that goes through resistor 1. Here's the current that goes through resistor 4. Now, we still have two others to consider. Right? So we know that total current goes through R1, right? And then it splits. And so we've just figured out that 0.28 amps is going this way, right? Which, if this coming through R1 is 0.58, we should be able to figure out at this point how much current decides to go up through L2, because we know how much goes through resistor 4. So we're just going to do some subtraction, right? So you have the total 0.58, and 0.28 of that is going through resistor 4. So the rest of this, 0.3, is going up through L2. Right, now, we don't really need that right now, but in the future we will. So I'll leave it there. And then it's going to get to this point, and it's going to split again. Okay, and so we have to figure out how much current is going through each of those. Now, in order to do that, we first need to figure out the potential drop over L2. Right, so I'm going to do this in a different color. Let's find the potential drop over L2. So that's going to be the current that goes through L2, which we just determined to be 0.3, times the resistance of L2. So V of L2 will be 0.3. I'm going to drop my units just because I'm running out of space, times the resistance of L2, which was 11. So, the potential drop over L2, right, this is something that will help you determine how much current is going through R2 and R3. This is equal to 3.3 volts. Okay, now, how does this help me? So 3.3 volts of energy gets used here, and now I should be able to determine how much potential is used in R2 and R3, because we know that the potential used through R4 is 4.46. And so the current that goes through here uses 4.46 volts of energy. And the current that chooses to go in either one of these paths up the middle has to use this same total amount of energy. So knowing that the LED uses this much, we can find how much each resistor will use, right? So let's do this. We'll do this back in green. So to find the voltage drop of let's do R2 first. This is going to be equal to 4.46 volts minus 3.3. So 4.46 minus 3.3 gives me the voltage drop over resistor 2 as being 1.16 volts. And this will also be the voltage drop over resistor 3. Again, because at this point, right, when current splits, it has a certain potential left. All of that gets used in R4 before it goes through LED 1. So all of that same has to get used through LED 2 and R3, or through LED 2 and R2, right? And so that's how I'm able to figure these out. So now I can go back and determine the current through each resistor, right? Same process. So I'm going to let's do R2 first. So this will be V2 equals I2 times R2. So the potential over V2 is 1.16 volts equals I2, which we're trying to find, times the resistance of resistor 2, which is 6. So the current through resistor 2 comes out to be 0.19 amps. Okay. And then you have a couple different things you could do to find the current through R3. I'm going to use the same process. Right? So I'm going to use V3 equals I3 times R3. I know this is 1.16. I'm looking for I3, and R3 is 10 ohms. So I3 comes out to be 0.1, let's round, 0.12. So there are your currents through each of your resistors. Now, R1 is the total current, right? Total current goes through here. So if you look at adding I2 and I3, they should equal I4, right? And since I rounded a little bit, right, you'll have some discrepancies there. But I am going to write these in because these are things we're going to need to know, I think, to find the voltage drop over the LEDs. Which one of them I think we already found. Actually, both of them we already found, so I'm not even going to write them. So part C asks for the voltage drop over each LED, and I already found that for L1. And you know L3 should be 0, and L2 we found here, right? So for part C, these should be things you've already found, right? So the voltage drop over LED 1, V1 is equal to 5.22. Voltage drop over LED 2, right? So this will be V2, is equal to 3.3. And voltage drop over LED 3 is equal to 0 because nothing's traveling through there. So these are your answers to part C.